Systems of equations. So in this unit, we're going to be talking about systems of equations. So we're going to be working with more than one equation at a time. So what is a system of equations? Systems of linear equations is a set of two or more linear equations in the same variables. So I'm working with two equations, or maybe three or four. We'll probably stick with two. That the variables in them are the same and represent the same thing. So if I'm looking at word problems, those two variables or three variables would represent the same thing. So if I defined my variable, they would mean the same thing. A solution to a system of equations is an ordered pair that is a solution to both or all of the equations in the system. So if there's more than one equation, if there's two or three equations, that ordered pair works in all of those equations. And we've looked at making a table to come up with solutions of equations. We've looked at making graphs. We have looked at using the intercepts to come up with solutions. So we have quite a few ways to come up with solutions for one equation. Now we're going to talk about coming up with solutions for two equations is what we're going to look at. So we're going to start by kind of getting an understanding of what this means by looking at a word problem. So here's the word problem we're going to work with to start with. Nick plans to start a home business producing and selling gourmet dog treats. He figures it will cost $12 in operating costs per week plus 50 cents to produce each treat. He plans to sell each treat for $2. How many treats does Nick have to sell to break even? All right, so let's figure out what's going on here. So he's going to be selling treats. It's going to cost him $12 a week in operating costs. So that may be that he's buying the materials that he's using to make the treats. That may be that his mom is charging him rent for all the mixers. That may be that he also has to buy packages to put the dog treats in, or stickers for whatever it is that he has to buy in a week. It's going to cost him $12 for that week. It also costs him 50 cents for every treat that he produces. So that actually might be the whatever ingredients he's putting into his treat. It costs him 50 cents to make one treat, but it costs him $12. No matter how many treats he makes, it's going to cost him $12 for that 1 week. So this is money that he has to pay. That's money that he has to pay to make the treats. He's only doing this so he can make some money, and he's going to sell the treats for $2 each. So he has money that he has to pay. That's going to be his costs. And then he also has money that he's going to be taking in. We'll call that's his income, or revenue is the other word you'll hear. So his income or revenue. So he wants to know when he's going to break even. So the break even point is the point when the cost equals the income or the revenue. So what's the amount of treats that Nick has to make so that the amount of money he's paid is the same as the amount of money that he has coming in. So he wants to know how many treats does he have to actually make in a week in order to be able to make any money. He doesn't want to sell 2 treats every week. He's not going to be really making enough money to make it worth his money and his time. So how can we figure this out? So we've got two things going on here. We've got how much he's paying, how much it's going to cost him to make these treats, and what his income is. So we're going to write two equations, one for each of those. First, we're going to define our variables. So he has two things going on. First, we're talking about how many treats he's making and how many dollars he is either paying or how many dollars he is either getting in as income. So how many treats he makes depends that changes how much it's going to cost him. How many treats he sells, that determines how much he's going to be getting in as income. So our two equations, one of the equations has to do with the cost. So one equation is the amount of dollars that he makes equals the $12 per week plus the 50 cents for each treat that he has to make. And his income, the dollars that he gets, is $2 times each treat that he sells. So here are two equations, and we're going to use those two equations in two different ways to figure out his break-even point. So first we're going to make a table, and this isn't really the most efficient way to do this because you'll notice my table is kind of long. But hopefully you'll see what's exactly going on as we make this table here. So what I've done is instead of making a table with 2 rows, I've actually made it with 3. So I've got my input here at the top. So I said how many treats is he making? So let's say he's making 1, 2, 3, 4. I did all the way up to 10 treats. Hopefully that he doesn't have to make more than that, or otherwise my table will be really long. So I made my input into up to 10 treats. And then I have 2 output rows. So I have a row for the cost. So if he makes 1 treat, it's going to cost him $12.50. It's going to cost him $12 for that weekly amount of cost, plus it costs him $50 to make that 1 treat. So I use this first equation to come up with this first row. So 1 treat costs him $12.50. 2 treats cost him $13. 3 treats cost him $13.50. Notice it's going up by 50 cents every time. Then I made another row for his income, so the dollars that he's making for his income. If he sells 1 treat, he makes $2. 2 treats, he makes $4. 3 treats, he makes $6. Does this make sense? It's going up by $2 every time. So every time he sells another treat, it increases by $2. So what I'm looking for here is where the cost that he has to pay equals the cost that he's getting in. So the dollars that it's costing him is equal to the dollars that he's getting for income. So you'll notice here that as I have these lower amounts of treats, it's always costing him more than he's getting. At 5 treats, it costs him $14.50, but he only made $10. That's a bummer. At 7 treats, he cost him $15.50, but he only made $14. You'll notice at 8 treats, we end up here where he cost him $16, but he's also going to make $16. So 8 treats is the magic number for him. 8 treats is where things start to tip. That's the break-even point. So if he sells anything below 8 treats, he's losing money. And if he sells anything above 8 treats, now he's going to make some money. So notice here at 10 treats, it costs him $17, but he made $20. So he's actually now have $3 to spend, which is pretty exciting. So the question was, how many treats does he have to sell to break even? He has to sell 8 treats. 8 treats will cost him $16 and get him an income of $16. So a table is one way to do this, but notice this is really cumbersome and rather awkward to do. So let's go back to something we've been doing with our equations with 2 variables. We've been graphing. So here I have a graph, and I graphed 2 equations on the same coordinate plane, which we haven't done that yet. That's kind of new for us here. So let's see what happens. So I took my first equation, which was how much it costs Nick. Here's my d equals 12 plus 0.50t. And I plotted these points. I took these ordered pairs here, and I plotted them. I could have also done my y-intercept and my slope. This has a y-intercept of 12 and a slope of 50 cents. So it goes, for every 1 treat, it goes up 50 cents. So I graphed those points here. And notice I made, for every one of those, I made a point on there. So I want to actually have a lot of points here because I really want to see where those 2 points intersect each other. Then I took my other equation, d equals 2t. This has a y-intercept of 0 and a slope of 2. So for every 1 treat, it goes up $2. And notice I made a lot of points here and graphed my line. And where it intersects, right here where those 2 lines meet each other, is 8, 16. Again, this goes back to an input of 8 treats gives me a cost of $16. So again, if he makes 8 treats, it's going to cost him $16, but he's also going to get an income of $16. So systems of equations, this is what we're looking at, taking 2 equations and finding one ordered pair, in this case 8, 16, that makes both of them true at the same time.